So we have one more comparison test we can deal with. We're going to talk about this continuing in our study of series and sequence. So essentially what we're going to assume here is we have two positive series or terms. And for all indices past some n integer value, so greater than some certain point. If we're dealing with these positive series and we say, well, that the nth term A divided by the nth term B, okay? So if we look at that limit as n approaches infinity of the ratio of the nth term of this positive term A over the nth term, a positive term B. So we have three situations. If we get a constant, situation one, we do the limit of this ratio of terms, and that constant is positive. So if we set this up as a limit and we get a positive constant, then we can state that either the series of A and B either both converge or both diverge. Okay? If we end up in a situation where that same limit of those nth terms is equal to 0, then what we can say, well, if we know the denominator converges, we can draw this conclusion. The numerator converges. And lastly, if that same limit of the ratio of the nth terms, if it is equal to positive infinity, and we know, again, that the series in the denominator diverges, then we could say, well, the series in the numerator diverges. So let's look at some examples here with our limit comparison test. All right, and so we're going to pick an nth term. For each of these, create a ratio, do the limit as n approaches infinity, calculate that, and we're going to be looking either for a positive constant, 0, or infinity. So here we have an example. The sum from n equals 1 to infinity of 2n plus 1 divided by the quantity n plus 1 squared. All right, so we got to figure out how to deal with this. Can we make it look like something we know? So let's consider what that, series looks like. So if I FOIL that denominator, this would be the same as saying my sum from n equals 1 to infinity of 2n plus 1. Foiling that gives me n squared plus 2n plus 1. And my terms, if I start listing them out, I've got 3/4 plus 5/9 plus 7/16 plus 9/25, and this keeps going. All right, so because we know all terms are positive, and remember that was a condition that we stated, as long as we have all positive terms, I'm going to let what we're dealing with, this guy, this is going to be a sub n. So I'm going to let a sub n equal 2n plus 1 over n squared plus 2n plus 1, because I'm looking at this and I'm going, okay, I'm going to choose to use my limit comparison test. And so as we think about our nth term, right, as n becomes very large, then we expect behavior if we get rid of those constants, such as 2n over n squared. So I'm just looking at those leading terms. These should be similar. And that, of course, we can simplify. That's equal to 2 over n, which looks like our harmonic series. And I'm just going to choose here, I'm going to choose to say 1 over n because that's my harmonic series. So what we assume is that this series is going to behave pretty similarly to my harmonic series. But this is a similar smaller, easy to deal with series, right? And remember, this harmonic series is divergent. All right. So what I'm going to do here is I'm going to let b to the n equal 1 over n. So let's set this up to use our limit comparison test. And the limit comparison test says, well, we're going to do the limit as n goes to infinity of my nth term for a, and a was 2n plus 1 over n squared plus 2n plus 1, divided by my nth term for b. Okay? So I've set this limit up. My a and b both represent nth terms from series. And I know b sub n is the nth term from my harmonic series, which is divergent. So let's see what happens if we simplify this. Do we get a constant? Do we get 0? Do we get infinity? And when I say constant, it needs to be a positive constant. So here I've got the limit. I'm just going to simplify this rational expression. Dividing by 1 over n is the same as multiplying by n. So I've got 2n squared plus n over n squared plus 2n plus 1. So this is the limit of a rational function. And when we think about limits of rational functions going to infinity, we think about using our comparison test for horizontal asymptotes. And we can see here that this guy is going to have a horizontal asymptote at y equals 2. So the limit as this rational function goes to infinity is equal to, which is a positive constant. So this is case 1 from our limit comparison test. And since the sum of b sub n is divergent, then we can state here that the sum of a sub n is also divergent. And we are done. So let's look at this series. We've got our sum from n equals 2 to infinity of 1 plus n times the natural log of n squared plus 5. So again, for us to use our limit comparison test, we have to know that all of the terms are going to be positive. N squared, I mean, we're always dealing with a positive n, but we're going to get n squared is a positive number, plus 5, another positive number. 1 is always positive. This n here is always going to be 2 or greater. And a natural log of n, is always going to be a positive number. Okay? So the natural log of anything past 1 would be a positive number. So we know that all of our terms are positive, and that lets me know I can use my limit comparison test. So I'm going to say let a sub n equal 1 plus n times the natural log of n over n squared plus 5. We know we have all positive terms, but what do we expect to happen? And can we simplify this a little bit? So what we say is, well, if n becomes really big, if that index becomes great, how do we expect this to behave? And this plus 1 and this plus 5, if we have a very, very large n, plus 1 and plus 5 are rather insignificant. So as n becomes infinitely large, we expect behavior such as n ln n over n squared, which I can cancel that out, and that would be the same as ln n over n. I'll write it here. We can reduce a common factor. Okay, so we expect this guy to behave like that guy. So let's think about how we are going to choose our b sub n term. So right now we're looking at n, ln n over n squared is basically equal to the natural log of n over n. And if we start listing out terms for ln n over n, what we see is that all of those terms are going to be larger than the terms for our harmonic series as long as we're dealing with an n greater than or equal to 3. And the harmonic series is divergent, right? So because this guy is divergent and it's smaller than ln n over n, this is also divergent by the regular comparison test, not the limit comparison test, by the direct comparison test. Okay, so ln n over n is divergent. We're going to use 1 over n here. So I'm going to continue down. I'm going to let b sub n be 1 over n. So when I use my limit comparison test, the limit as n goes to infinity of my original term, was my original nth term for a, is going to be 1 plus n ln n over n squared plus 5. So we have all of that divided by 1 over n. And I'll simplify this. This is now the limit as n goes to infinity, n plus n squared ln n over n squared plus 5. All right, so this is the limit to infinity of a rational function. And in order for us to do that, we divide everything by the highest power of n, or the highest power of x in the denominator. In this case, we're using n. So n divided by n squared, got 1 over n. N squared ln n divided by n squared gives us just ln n. N squared over n squared is 1, and then I have plus 5 over n squared. So if I look now at evaluating this limit at infinity, I've got 1 over infinity plus the natural log of infinity over 1 plus 5 over infinity squared. And we know that both 1 over infinity and 5 over infinity squared go to 0. So essentially we are dealing with the natural log of infinity. And the natural log of infinity goes to infinity, right? Because if you think about that graph of a natural log, it goes like that. So as n becomes infinitely large, the graph becomes infinitely higher, goes to positive infinity. So what we can now say is by part 3 of our limit comparison test, what we know is that if the limit as n goes to infinity of the nth term of a over the nth term of b equals infinity, then we can say a sub n, or the sum of a sub n, I should say, that series diverges.